In section 12.4, what we do is go through a few steps to break down and analyze a function to know a lot more about it, giving us a sense of what its graph will look like and how the function will behave. And in the handout, I have listed some of the steps that we're going to go through. In the first step, we're going to list out things like finding the domain, the intercepts, and the asymptotes, if asymptotes are relevant to the function. In step 2, we're going to continue to analyze it, but by using the first derivative, f prime. We'll find f prime, we'll find the critical numbers, and we'll go through checking the intervals to find the sign, positive or negative, to help us know where it's increasing or decreasing. Then we're going to do the second derivative, do the same kind of stuff we would do with the first derivative, finding out where it's positive, where it's negative, and that can help us know about concave up versus concave down and the inflection points. And then finally, we'll draw a sketch as best we can using all the information we have, increasing, decreasing, local maximums, minimums, and concave up, down, and inflection points. Let's go through these steps and find the information about the function. So for the first step, what I'm going to do is to find the domain. So the domain, what we need to do is set the denominator equal to 0 and solve. So x minus 2 equal to 0. We'll add the 2 over and we'll write it as x equals 2. What that means is that the domain is all real numbers except for x equals 2. Due to the fact that the denominator being 0 would not be a possibility, so we leave that part out of the domain. The second thing we're going to do is define the intercepts, starting with the x-intercept. To find the x-intercept, we set the whole function equal to 0 and solve, which in a case like this where we have a denominator would involve technically multiplying both sides by the denominator x minus 2 so that we can cross it out here. That really just will leave us the numerator x minus 1 set equal to 0, which solving would give us x is equal to positive 1 as our x-intercept, or that would be the coordinates 1, 0. You might notice that ultimately the denominator had no real influence here since we got rid of it anyway. So in the long run, finding the x-intercepts for these kind of functions would really just involve using the numerator and solving it equal to 0. In the case of the y-intercept, we plug 0 in for x. 0 minus 1 over 0 minus 2 would equal to positive 1 over 2, or the coordinates 1, 1/2. The next thing we're going to do is to find the asymptotes, which does make sense for a function like this to have asymptotes. The vertical asymptotes we found by setting the denominator equal to 0. So again, technically the thing we did earlier for the domain, also x minus 2 equal to 0, would give us x is equal to positive 2. In this case, again, that's outside the domain, but it also represents a vertical asymptote line for the function. We also have the horizontal asymptotes, and horizontal asymptotes, we divide leading coefficients of numerator denominator when the degree is the same on top and bottom. In this case, the degree on top and bottom is both x to the first power, so we can just divide the leading coefficients here. Both of them are 1s. 1 divided by 1 is 1, so we say y equals 1 is the equation of the horizontal asymptote. In the second step, we're going to find where it's increasing, decreasing, and the local maximum and minimum. To do this, we need to find the first derivative f prime of x. Before I do that, let's recall what the original function f of x looks like. X minus 1 divided by x minus 2. We're going to have to take the derivative of this. We're going to have to use the quotient rule in order to do that. Again, the quotient rule goes low d high minus high d low all over the square of what's below. So let's use that here to find the first derivative. F prime of x will be equal to, we write low x minus 2 d high. Derivative of the thing on top, the x minus 1, is just 1. Minus high, x minus 1 d low. Derivative of what's underneath is just 1. All over the square of what's below. We'll simplify what's on top. Up on top we'll have x minus 2 minus x plus 1 all over x minus 2 in parentheses all squared. And that's equal to, on top, just negative 1 divided by x minus 2 all squared. Okay, and in order to solve from here to find the numbers we need, the critical values, we do two things with the derivative. We're going to take the derivative f prime of x and consider setting that equal to 0. But we also need to consider where f prime of x does not exist, which does have some bearing on the discussion here. Starting with where f prime is equal to 0 would mean trying to take this whole fraction thing from the derivative and set it equal to 0. Which I did something similar a second ago when I did the intercepts. I multiplied both sides by the denominator and got rid of it. Let's do that here also. Now, a different thing happens here because only thing that's on top is negative 1, and that would make it look like negative 1 equals 0. Well, it doesn't really solve, so that's kind of a dead end as far as solving here. No solution trying to solve it here. So no values will make the derivative equal to 0. On the other hand, for does not exist, that all revolves around the denominator and where the denominator is equal to 0. Just like we did with the domain and the vertical asymptote, we know x equals 2 causes the denominator to equal to 0. And it actually didn't make any difference here that it's raised to the second power. We just take what's inside there, the x minus 2 in the parentheses. It still solves for x equals 2. That's our critical number. We only have one critical number in this case. What we do with that critical number is we consider the number line here. We put our critical number inside there and consider some test values on either side. I'm going to use the test values, but you can use different numbers. I used 1 and 3 as test values. And we're going to plug those test numbers in to the derivative and see what happens. What we're going to do now is plug our test numbers into the first derivative and see what happens. So our test numbers of 1 and 3 get plugged in. For positive 1, it'll look like negative 1 over 1 minus 2 raised to the second power, which turns into negative 1 divided by positive 1, or just negative 1. Since this is negative for the first derivative, that means it's decreasing. For positive 3, we'll plug in that number for x, but it turns out we'll still have negative 1 divided by 1, still just a negative number, still decreases on either side. So we're going to say that this thing is always decreasing. It's decreasing from negative infinity to positive infinity. And there are no local maximum or minimum points. For the next part, we're going to do the concavity and inflection points. To do that, we're going to need to find the second derivative, f double prime of x. Let's write down the first derivative here was negative 1 divided by, in parentheses, x minus 2 raised to the second power. Before trying to take the derivative here, I'm going to rewrite this as negative, parentheses, x minus 2 raised to the negative 2 power. Now trying to take the derivative of this is going to force us to use the chain rule. So f double prime x would equal to negative, I'll go ahead and write here negative 2, because I'm going to bring that negative 2 out to the front, subtract 1 away from the exponent, and write x minus 2 in parentheses raised to the negative 3 power. Technically, we do have to multiply by the derivative of the inside, but that's just 1. So to recall, chain rule means we do the derivative of the outside times the derivative of the inside. In that case, we would write it as now just positive 2 parentheses x minus 2 and raised to the negative third, or 2 divided by x minus 2 all raised to the third power. So we're going to take some of the same steps. We're going to figure out if we can solve this equal to 0, or is there anything for where the second derivative does not exist. You'll probably find that it looks pretty much similar to what the first derivative did. When we tried to solve it equal to 0, we'll get the same exact circumstances, even though things have changed slightly. Even if I try to get rid of the denominator by multiplying it to both sides and crossing it out here, we're still going to be left with a numerator that tells us absolutely nothing as far as the solving. 2 equals 0, so no solution here. If you want to take a shortcut, if you know that the numerator isn't going to solve, then there's really no reason to go any further with this part. As far as does not exist, same number from the denominator, x is equal to 2. If you were to take the denominator x minus 2 inside the parentheses and set it equal to 0, it's still the same number. We treat that again like we did the critical number a second ago, but we're basically going to be retreading some of the same territory here, picking out the same test values 1 and 3, but we'll be plugging these into the second derivative instead of the first derivative. So let's do that here. If we plug in the positive 1, it would look like 2 divided by 1 minus 2 raised to the third. I came out with something that looked like 2 divided by negative 1, so negative 2 is the number we would get here. Turns out now that that's a negative number, and a negative in the second derivative means that this is concave down. If we plug in the 3, it's going to make it look like 2 divided by 3 minus 2 raised to the third, which is equal to 2 divided by 1, or in this case positive 2. Positive, concave, up. Technically, while it does switch the direction here at 2, usually we would call this an inflection point. However, this is a number we came from the derivative where it does not exist. So even our original function, the second derivative plus even the first derivative and the original function does not exist for x equals 2. So we don't actually have any inflection points in this case. So sometimes we still use that number, but again, it's just to help us find things like the critical numbers, and if it turns out to actually change the concavity here, won't be able to call it an inflection point. If the function did exist there, then we could use that number for an inflection point. I will write down here that this thing is concave down on the interval from negative infinity to 2, and this thing is concave up on the interval from 2 to infinity. Once I get all this information down, we're ready to draw something for it. So let's do that here. We'll start with our asymptotes, which we had a vertical asymptote going through x is equal to 2. We had a horizontal asymptote going through y is equal to 1. And we had our intercepts. We had a x-intercept at positive 1 and a y-intercept at 0.5 or 1/2 right here. And we know that it will be decreasing and concave down on the left side of 2. So we'll draw it kind of curving downward like this. And then it's decreasing and concave up on this side. The only way to make that happen is to open it up the other direction from the other curve inside the other asymptotes. So we have to keep it in mind that it can't really merge into those asymptotes. It just gets really close to them. Here's a function that goes f of x equals 3 plus 7e raised to the negative 2x power. Now, before I jump into all the analysis of this particular function, let me just mention in general some of the behaviors of exponential functions. Exponential functions usually only have this going on with them, unless there's some extra things involved, which is what we kind of have here. They pass through here at the coordinates of 0, 1, and they never touch the y-axis. Technically, that's a horizontal asymptote for them. And we technically will see something very similar to that here. I will go through the full analysis of this one with the different testing that we've done up till now, but that's one thing to keep in mind. They also have domains which are all real numbers, from negative infinity to positive infinity. So if we start out with the different steps that are outlined in the guidance that at the beginning of the section, and we started with the domain, well, that's automatically going to be all real numbers in the case of a exponential function here. On the other hand, the x-intercept, if we try to find that, we might not be able to go very far actually. If you look at the graph on the other side, there are no x-intercepts, but there are cases where they could have an x-intercept. And if we were to do the normal process of setting the function equal to 0 and solving, it would look something like this. We would have to try to solve for x. I would, in this case, subtract the 3 over and write it as 7e raised to the negative 2x is equal to negative 3. And then I would divide out the 7 to both sides. That would make it look like e raised to the negative 0.2x is equal to negative 3 divided by 7. In cases where we have e and we're trying to solve, we put the ln on both sides, because the ln and e are inverses, so you can cross those out here, leaving it as just negative 0.2x is equal to ln of negative 3 over 7. And the full solution process here would make us have to divide out the number in front of the x, the negative 0.2, to both sides. So that would be x is equal to ln negative 3 over 7 divided by negative 0.2. Now, if we try to put this in the calculator and figure out if it's equal to something, it's actually not going to work. And the reason why this doesn't work is technically the ln of a negative number is undefined. So what that basically means for us is there are no x-intercepts here. We could do the y-intercept though. If we plug in a 0 for x, it would look like 3 plus 7e raised to the negative 0.2 times 0. We can plug that in the calculator and it comes out with actually a nice number of just 10. So the coordinates 0, 10 are where it crosses the y-axis. Now, if you are asked about asymptotes, the thing is, for rational functions, there are no, for exponential functions, for exponential functions, there are no vertical asymptotes. However, like I mentioned there at the start, there could be a horizontal asymptote. And there is actually in this case, if we consider the basic shape of an exponential function, where the horizontal asymptote starts right underneath it. This particular function has 3 plus, And that 3 in front causes what we call a transformation, shifting the graph up by 3. So if we were to take the graph and shift it up by 3, it would move something like this here, meaning that the horizontal asymptote actually turns into the line y equals 3, since it moves it up 3 up higher. So that's our answer for horizontal asymptote, is y equals 3. So if you do see that in the homework, a similar example, you can actually just use that number that's being added there, like the 3 plus, to determine what the horizontal asymptote would be here. Okay, now for the step 2, we're going to need to find the first derivative, because we're going to find the critical numbers and where it's increasing and decreasing. So starting with the original function here, what we're going to do first is find f prime of x. F prime of x in this case would equal to 7e raised to the negative 0.2x times the derivative of the negative 0.2x, just the negative 0.2. And if we multiply these numbers together here, we're going to find that this is equal to negative 1.4 e raised to the negative 0.2x. We're going to do the two things that we usually do with our derivative. We're going to try to set it equal to 0 and solve. So setting the first derivative equal to 0. And we also want to check if the first derivative does not exist. Now I'll go ahead and throw in here that since it's an exponential function, it always exists. So this is not a function where we need to worry about whether or not it exists or not exists. We'll only need to think about the derivative set equal to 0. And what I did to solve that here is I divided both sides by negative 1.4. So we're going to write that as e raised to the negative 0.2x is equal to 0. To which we try to take the natural log of both sides and see what happens, in which something weird is going to happen here. We take the natural log, well, it does allow us to get rid of ln and e here, leaving just the negative 0.2x. But on the other side, ln of 0 actually doesn't work. If you try to plug that in the calculator, it'll say undefined. And that's because logarithms are only defined which are for numbers which are greater than 0. So we get actually no solution here as far as solving the derivative set equal to 0. And you're basically going to be able to see that in any of the exponential functions you receive in a lot of cases. So that means there are no critical numbers in this particular instance here. Well, that doesn't give us much to go by, but what all we'll do here is just go to the number line, leave it empty, and just pick out any random number we want to as a test value. We'll plug that number in for our first derivative and just observe what happens with that. So plugging this into the first derivative here, plugging in the value of 1, we would see it looks like negative 1.4 e raised to the negative 0.2 times 1, which I just got a decimal for it of negative 1.1. So it's negative, it's decreasing. So no matter where you go, this function will always have a negative derivative and it will always be decreasing. The next step, we're going to find the second derivative. So before we find the second derivative, let's consider the first derivative here that we just found. F double prime of x would be equal to negative 1.4 e raised to the negative 0.2x times negative 0.2, which again, when I multiply these numbers together, we'll get a positive 0.28 e raised to the negative 0.2x. So if we were to set it up like we did before with the second derivative, in this case equal to 0, or we ask the question, is there anything where the second derivative does not exist? We're actually going to find it's almost the same as the last derivative. If we try to set this equal to 0, do all the steps that we did before, we'll find it's the same exact situation. We try to take the ln of 0 and it fails to solve. And just like the first derivative, the second derivative always exists. So we don't have to do anything more there. No critical numbers. Let's just pick out any random number, plug it into the second derivative, and see if we have it increasing or decreasing. So I just chose 0 as an example here of a test number, and plug that into the second derivative. When I plugged in 0 here, I made it look like 0.28 e raised to the negative 0.2 times 0. That came out to be just a positive 0.28. Being that it's positive, we know it'll be increasing, concave up. Being that it's positive, we know it'll be concave up. So that means this thing is concave up basically across the entire span of the real number line. It's always concave up. With that said, we should be able to know everything we need to know about this function here. We got the horizontal asymptote, which I mentioned was at y equals 3. We got our y-intercept, which was way up there at 10. And so it's concave up, and we wrote down that it's always decreasing. So it's going to come down through this intercept up here. Being concave up, it's going to kind of stay concave up as it travels through the points up here.